This is 6.2.1.3. This is page 8. We'll continue our DTFS using inspection of the synthesis equation. Now we are given xn to be this formulation. It has a DC term. It has a complex exponential at 0.2 pi with a phase shift of minus 0.5 pi. And now it has a cosine term at 0.25 pi and a phase shift of pi over 3. We now know that if we want to analyze this equation by direct inspection, we have to decompose this cosine into complex exponential. So using the Euler's formulation, the cosine is broken down into half of this complex exponential plus e minus this complex exponential. What about minus 0.5 pi? 0.5, the constant. Actually, minus 0.5 can be represented as a complex exponential as well. In fact, it is the complex exponential with amplitude 0.5 but with omega equals to 0. That means the frequency of this complex exponential is 0 because e to the power j0n is still 1. But this is minus 1. So how do we get minus 1? We introduce a phase shift of pi. Maybe I'll explain here. This is the complex plane, the real and the imaginary. Let us have this phasor as half. This is minus half. This guy is half. This guy is 1 on the right hand side because this is the origin. This is half, this is 1, this is 2, and so on. This is minus half. So minus half is the same as the magnitude half with phase shift of pi. Or in fact, if you prefer, is half e minus j pi as well. So that you can introduce this angle. But it doesn't matter whether it's pi or minus pi, you'll still get minus half. So in here, I simply use magnitude 0.5 with a phase shift of positive pi. Now, we have this form of xn, and now it looks like it is all complex exponential. So the problem now is to identify which complex exponential at which frequency so that we can now find different ck's. To find the fundamental period, we will first go to each of these complex exponential and find its period. The period for 0.2 pi for this guy is n equals to 10. And 0.25, the period n equals to 8. So we now need to find the least common multiple between these two periods. So this is 10, 20, 30, and 40, and 50 for different n's. For n equals to 10, there will be 1 period, n equals 20, there will be 2 period, and so on. What about 8? So for this 0.25 pi, we will take 8 samples and we will complete one cycle. 16, 24, 32, 40, 48. So we have now found this common period. 40 is the common period between these two complex exponential. We will use n equals to 40 because the DC term doesn't matter. So the only interesting complex exponential is 0.2 pi as well as 0.25 pi. We have now found n equals to 40 and we can use omega naught equals to 2 pi divided by 40 to represent the fundamental complex exponential frequency that we are interested in, which is pi over 20. So now we can find the associated k because we are interested in 0.2 pi. So the associated k for 0.2 pi is k is equals to 4. And what about 0.25 pi? It is k equals to 5. So the interesting thing will happen at k equals to 4, k equals to 5, as well as k equals to 0 for the DC term 0.5. So let us go and identify. This is k equals to 0, k equals to 4, and k equals to 5. The rest of the terms are 0 until k equals to 35. Let's see why. Why is there something interesting at k equals to 35? It is because of this cosine. Remember, the cosine has 0.25 pi as well as minus 0.25 pi. What is minus 0.25 pi? Then you will be thinking that there will be a minus k. Well, it can be a minus k, or we can also use the positive frequency. So actually, the index k equals to 40 is the same as k equals to 0. So k equals to 35 is the same as k equals to minus 5. So this pair are the pairs of magnitude for the complex exponential representing the cosine. One is for the positive frequency 0.25 pi, and one is for the negative frequency minus 0.25 pi. But minus 0.25 pi is equivalent to 1.75 pi, and that is why it is sitting at k equals to 35. Now, most of the time I will ask you to plot with respect to k as well as with respect to the real omega from 0 to 2 pi. So now we can see at this point it is exactly at 1.75 pi for this horizontal frequency, 1.75 pi. Because one interval is pi over 20 equals to 0.05 pi. Now let's use this figure to reconstruct this complex exponential. We will use the last equation over here. So let us find first the DC term. The DC term is 0.5 with magnitude at omega equals to 0 and phase shift of pi. Let's see what is it. So we have magnitude here and we have phase here. So the magnitude should be minus 0.5, or the magnitude should be 0.5, so we get 0.5 here at omega equals to 0, and the phase is minus pi. Now what about here? This frequency is 0.2 pi. At 0.2 pi we have a magnitude of 3 as well as a phase shift of minus 0.5. This is correct. We have a magnitude of 3 at frequency 0.2 pi with a phase shift of minus 0.5. And the last one, both the magnitude is 1. The frequency is at 0.25 pi. The frequency is at minus 0.25 pi. The associated phase shift is plus pi over 3. This guy, the associated phase shift is minus pi over 3. So let's see. At this frequency, which is 0.25 pi, the amplitude is 1. At this frequency, 1.75 pi, which is equivalent to minus 0.25 pi, the magnitude is also 1. The phase is pi over 3, so this is 1/3, 0.333. Remember that we are plotting the vertical axis with respect to pi, so this is plus 1/3. The other guy is sitting at minus 1/3. So again, now we can see that the DTFS representation is nothing but a very compressed graph showing the magnitude and phase with respect to different frequencies, showing the magnitudes that is important, that have values, and the phase that have values. Remember that phase normally is very noisy. Here again I use the trick that if the magnitude is less than a very small value, I will make the phase 0. So this is the DTFS of complex exponential by direct inspection. Thank you.